We're now going to discuss a first proof by induction. We have a lemma that says that if we have k vectors in Rn and a linear transformation that transforms these vectors from Rn to Rm, then L of the sum of the vectors is the same as the sum of L applied to the individual vectors. It is tempting to say that this is simply obvious, since L of u plus v is equal to L of u plus L of v. But what we're going to do is prove this rigorously. Whenever one tries to prove a result for a general k, where k is a natural number, one often uses a technique called proof by induction. A proof by induction has a very specific structure. It's always good to start a proof by indicating what technique you're going to use. In this particular case, we're going to say that we're going to do a proof by induction, and the variable on which we're going to do induction is the variable k. You then start by proving the base case. The base case is a case where k is typically small. In this particular case, we're going to choose k equals 1. For this case, we must show that L of v0 is equal to L of v0. That's trivially true. The next thing you must do is state the inductive hypothesis and then prove the inductive step. Stating the inductive hypothesis means that you say, let's assume for a big K greater than or equal to 1, it is the case that L of v0 plus v1, etc. through vk minus 1 is the same as L applied to the individual vectors and then summed. So we're going to assume that this is true for little k equals big K. And what we're now going to prove is that if we assume that that's true for little k equals big K, then it's also true for k equals k plus 1, big K plus 1. Let's assume that big K is greater than 1 and k is equal to big K plus 1. Then if you look at the expression L of v0 through vk minus 1, that's the same as L of v0 plus v1 through v sub big K. We can split off the last term and explicitly expose vk minus 1. And we can then put parentheses around the first big K vectors. Now we know that if we sum big K vectors, we get another vector. So that's just L of one vector plus a second vector. Therefore, because L is a linear transformation, we know that that's just L of the first vector plus L of the second vector. And because of the inductive hypothesis, we now know that L of v0 plus v1 plus etc. through vk minus 1 is the same as L of v0 plus L of v1 etc. We assumed that. Now, we can also take the parentheses around that away because of associativity of vector addition, and therefore we end up with the desired result. And then we simply say that by the principle of mathematical induction, the result holds for all k. So here's the idea. The base case shows that it's true for k equals 1. v0 is equal L of v0 is equal to L of v0. The inductive step says that if it's true for k equals to 1, then it's also true for k equals 1 plus 1, which of course is equal to 2. So then we know that so if it's true for k equals 1, then we know that L of v0 plus v1 is the same as L of v0 plus L of v1. But we know that it's true for k equals 1, so therefore we conclude that it's true for k equals 2. The inductive step again implies that if the result is true for k equals 2, then it's also true for k equals 3. Since we just reasoned that it's true for k equals 2, we now know that it's also true for k equals 3. So L of v0 plus v1 plus v2 is the same as L of v0 plus L of v1 plus L of v2. And you can continue this for all n, and therefore we know it's true no matter how many vectors we add together.